Introduction to dialectics, dialectic polarization, dialectic polarizability, susceptibility, dialectic constant, types of polarization, frequency dependence of polarization, internal field in a dialectic, classes and Mosotty equation, and applications of dialectics. So these are the topics in dialectics. Now coming to the introduction about dialectics. So electrical circuits use insulator materials in various forms. Capacitors use dielectrics as medium. The dielectric materials, which are also known as insulators, constitute a very important group of electrical engineering materials. They are characterized by dielectric constant, dielectric loss, dielectric strength, and resistivity. The two properties, namely dielectric constant and dielectric loss, are strongly frequency dependent. The main properties of dielectric materials are dielectric constant and dielectric loss. Both are strongly frequency dependent. The use of a dielectric in a specific application is dictated by the frequency of the applied voltage. The dielectric loss is required to be a minimum so that the performance of the dielectric does not deteriorate with time. Ferroelectrics are ceramic dielectric materials which exhibit very high dielectric constant and low dielectric loss. They are used in making miniature capacitors. Piezoelectrics are ferroelectric, such as ferroelectric materials having very interesting properties. Mechanical deformation is produced in them in response to electrical force, and electrical effects are produced in response to mechanical forces. The two piezoelectric effects are vastly exploited in all areas of technology, and the dielectric loss manifests in the form of heat. The dielectric heating can be employed in cases where heating by other means is difficult or is not possible. It finds application in the fields such as food processing, mainly food processing related. Insulators are used in microwaves. Okay, now coming to the here, dielectrics are insulating materials. They do not possess free electric charges and hence do not conduct electric current. The forbidden energy gap in dielectrics is large, which prevents thermal excitation of electrons from valence band to the conduction band. Even externally applied electric fields fail to excite the electrons. Dielectrics constitute a very important group of electrical engineering materials. You know that materials are characterized as three forms: conductors, semiconductors, and insulators. Okay, so now coming to insulators, insulators are nothing but dielectric materials. Okay, they do not possess free electric charges. So you know that conducting materials are having free electrons in the outermost shells, whereas in uh, insulating materials does not possess free electric charges and hence do not conduct electric current. Okay, the forbidden energy gap in dielectrics is large, which prevents thermal excitation of electrons from valence band to the conduction band. Why? Because forbidden energy gap is very large in conducting material in dielectrics. Okay, that is even externally applied electric fields fail to excite the electrons. Dielectrics constitute a very important group of electrical engineering materials. They are characterized by dielectric constant, dielectric loss, dielectric strength, and resistivity. Okay, the main characteristics of dielectric materials are dielectric constant, dielectric loss, dielectric strength, and resistivity. The dielectric loss manifests in the form of heat. Already I told you that the dielectric loss manifests in the form of heat. The dielectric heating sometimes can be effectively employed, particularly in the cases where heating by other methods is difficult or impossible. Now, dielectrics are electrically non-conducting materials such as glass, ceramics, polymers, and paper. So, dielectric materials are non-conducting materials. And those are examples of dielectric materials are glass, ceramics, polymers, and paper. When their role is to provide electrical insulation, the main role of dielectric materials are to provide electrical insulation. They are called as insulators. When they are placed in electric fields, they modify the electric fields they they themselves get polarized, as a result of which they act as stores of electrical charges. Okay, stores. So when the dielectric materials are placed in external electric fields, they modify the electric fields and they themselves get polarized, as a result of which they act as stores of electrical charges. When charge storage is the main role, the non-conducting materials are called as dielectrics. So dielectric materials are mainly used to store electric charges. So dielectrics are generally non-metallic. mm, when charge storage is the main role, the non-conducting materials are called as dielectrics. Dielectrics are generally non-metallic. They have high resistivities ranging from 10 to the power of 10 to 10 to the power of 20 ohm meter. Okay, so dielectrics are generally non-metallic and they have high resistivities ranging from 10 to the power of 10 to 10 to the power of 20 ohm meter. So coming to the main definitions, dielectrics. First one is electric dipole. So electric dipole means a pair of equal and opposite charges separated by a small distance are constitute an electric dipole. So electric dipole means a pair of equal and opposite charges separated by small distance are constitute an electric dipole, which is shown in figure. Which is shown in figure 1. See this one. Two equal and opposite charges. This one is a negative sign, negative charge, and this is a positive charge, negative and positive charge. So these two charges are separated by a fixed distance r, that is very small distance, constitute an electric dipole. So now coming to electric dipole moment. Okay, this is an electric dipole. Two equal and opposite charges separated by a fixed distance constitute an electric dipole. Now coming to electric dipole moment, the electric dipole moment is defined as the product of the magnitude of one of the charges and the distance of their separation. It is denoted by mu. Electric dipole moment is denoted by mu, and the definition is the electric dipole moment is defined as the product of the magnitude of one of the charges and the distance of their separation, and it is denoted by mu, that is mu is equal to q into r. Okay, the product of the charge and the distance. Okay, any of the charge, that is mu is equal to qr. Okay, where q is the magnitude of one of the two equal charges and r is the distance between them. The dipole moment is a vector quantity and it is directed from the negative to the positive charge. See this one. This is a dielectric dipole moment. Electric dipole moment is a vector quantity and the direction is from negative to positive charge. And this is arrow mark. So this represents the direction of the electric dipole moment. It is a vector quantity and it is always from negative to positive charge. Okay, and its unit is debye. 1 debye is equal to 3.33 into 10 to the power of minus 30 coulomb meter. 1 debye is equal to 3.33 into 10 to the power of minus 30 coulomb meter. So that is electric dipole moment. Now coming to types of dielectrics. Depending upon the molecular structure, dielectric materials are classified as two types. One is polar dielectrics and another one is non-polar dielectrics. So depending upon the molecular structure of the materials, here molecular structure of the materials are classified as polar dielectrics and non-polar dielectrics. So polar dielectrics means in certain molecules, the effective centers of the positive and negative charges do not coincide even in the absence of the electric field, and hence every molecule possesses a dipole moment. Such materials are called as polar dielectrics. So polar dielectrics means even in the absence of external, so in certain molecules, the effective centers of the positive and negative charges do not coincide even in the absence of the electric field, and hence every molecule possesses a dipole moment. Okay, so how the material, dielectric material is to be polarized means whenever the material is placed in an external electric field, then the two charges are separated by a fixed distance. Okay, that is called electric dipole. Okay, how that means the material gets polarized. That is called the material gets polarized. So in the absence of external magnetic field, in certain materials, the positive and negative charges do not coincide. Okay, and hence every molecule possesses a dipole moment. Such materials are called as polar dielectrics. Okay, such materials called as polar dielectrics. In the absence of the electric field, the electric dipole moments of individual molecules are randomly oriented. Hence, the net dipole moment of the dielectric is zero. Okay, so in the absence of the electric field, the electric dipole moments of individual molecules dipole moment mu tend to align with the electric field because of the torque experienced by the dipoles. Okay, here see this one, polar dielectrics. Okay, so in the absence of external magnetic field, okay, the molecules possess each molecule possess some dipole moment. Okay, but in the absence of external field, all the dipoles are tend to align in different directions. So that's why the net dipole moment of that particular dielectric material becomes zero. Okay, whenever you are applying certain external field, that means if you are applying electric field externally, so then the dipole moments, electric dipole moments of all the charges tend to align with the electric field in the direction of the applied electric field because of the torque experienced by the dipoles. Okay, ikkada chudandi. So this one, whenever, so positive, this one is positive, so this is also, so H2O. Okay, so this is a structure of H2O. So this one, see this one, mu1 of this one, and that means magnetic dipole, so electric dipole moment of this molecule as well as the electric dipole moment of this one. So this is called the net dipole moment of both. So mu is equal to mu1 minus mu2. So in the absence of external electric field, the net dipole moment becomes 0 because they are aligned in two different directions. So example H2O, CO2, N2O2, NH3, etc. These are examples for polar dielectrics. Okay, when non-polar dielectrics means in some dielectric materials the effective center of the negative charges distribution coincides with the effective centers of the positive charges. They are called as non-polar dielectrics. When an electric field is applied, the molecules are deformed, resulting in charge separation. Consequently, dipole moments are induced by the field, that is external magnetic field, which is shown in the figure 3a, 3b. Okay, so in the absence of external magnetic field, not magnetic, in the absence of external electric field, both the charges are coincide with each other. So here this one, no field is applied. Okay, when the field is applied, then the both charges, positive and negative charges, are separated by a fixed distance and a net dipole moment is arised within the material. Okay, so examples are H2, N2, O2, C6, H6, etc. So non-polar dielectrics means in some dielectric materials the effective centers of the negative charge distribution coincides with the effective center of the positive charge distribution, positive charges. They are called as non-polar dielectrics. Both are coincides in the absence of external electric field. When an electric field is applied, the molecules are deformed. So resulting in deformed means when an external field is applied, then they are get polarized. So deformation happens within the material. So positive charge and negative charge both are separated by a fixed distance whenever the field is applied. That is called polarization. Consequently, dipole movements are induced by the field. So which is shown in figure 3b as well as 3a. Okay. So these are examples. So these are the examples. Examples are H2, N2, O2, C6, H6, etc. Now coming to dielectric constant. Dielectric constant. The chief property of a dielectric is its dielectric constant epsilon r, which is also called as the relative permittivity. It is a measure of the extent of electric stress absorbed by the material when subjected to an external electric field. It is a measure of the polarization in the dielectric material. It is defined as the ratio between the permittivity of the medium to the permittivity of the free space. That is epsilon r is equal to epsilon by epsilon naught. Okay. So the main property of a dielectric is it's a dielectric constant. It is denoted by epsilon r. Okay, dielectric constant is denoted by epsilon r, which is also called as the relative permittivity. So dielectric constant is also called as relative permittivity. It is a measure of the extent of electric stress absorbed by the material. Electric stress absorbed by the material when subjected to an external electric field. Means whenever a material, dielectric material is placed in an external field, then the material absorbs. What happens? So positive and negative charges both are separated అని చెప్తున్నాము. ఎందుకు సెపరేట్ అవుతాయి? Those positive and negative charges are absorbed some electric field. సో కొంత ఎప్పుడైతే ఎక్స్టర్నల్ ఎలక్ట్రిక్ ఫీల్డ్ ని అప్లై చేస్తామో ఎక్స్టర్నల్ ఎలక్ట్రిక్ ఫీల్డ్ ని తీసుకొని ఆ టూ చార్జెస్ గెట్ సపరేటెడ్. ఓకే, మీన్స్ ఎలక్ట్రిక్ ఫీల్డ్ ఇస్ స్టోర్డ్. ఎలక్ట్రిక్ ఫీల్డ్ అనేది స్టోర్ అవుతుంది టూ చార్జెస్ ఎప్పుడైతే సపరేట్ అవుతున్నాయో. సో దట్ మీన్స్ దోస్ అబ్జార్బ్ some electric field which is externally applied by the dielectric material. Okay, so that storage of energy, that means stored electric field is measured by the dielectric constant. So it is a measure of the extent of electric stress absorbed by the material when subjected to an external electric field. So it is a measure of the polarization in the dielectric material. So what is polarization means? Polarization means whenever a dielectric material is placed in an external magnetic field, then those two, then the charges. So actually in insulating materials and dielectric materials, both negative and positive charges are coincide, bound together. ఓకే, రెండు పాజిటివ్ అండ్ నెగిటివ్ చార్జెస్ ఎలా ఉంటాయి? రెండు ఒకదానికి ఒకటి బౌండ్ అయిపోయి ఉంటాయి. సో వెన్ ఎవర్ యు ఆర్ అప్లైయింగ్ అన్ ఎక్స్టర్నల్ ఎలక్ట్రిక్ ఫీల్డ్, దెన్ దోస్ టూ చార్జెస్ ఆర్ గెట్స్ సెపరేటెడ్. See this one. So those two charges here, this is a dielectric material, the absence of external magnetic field. Both positive and negative charges are gets coincide with each other in the absence of external magnetic field. Sorry, external electric field. When you are applying certain electric field, then what happens? Both charges, positive and negative charges, are gets separated. So how these two charges are separated means those two charges absorbs some external electric field which is applied externally. So then those two are get separated. Means the material here, material said to be polarized. Okay, so that that electric field which is absorbed by the dielectric material is measured by its property, that is dielectric constant. Okay, dielectric constant is a property which is used to measure the electric field which is absorbed by the dielectric material, and it is denoted by epsilon r. Okay, it is a measure of the polarization in the dielectric material. It is defined as the ratio between the permittivity of the medium to the permittivity to the permittivity of the free space. Okay, it is a measure of the polarization in the dielectric material. It is defined as the ratio between the permittivity of the medium to the permittivity of the free space. That is epsilon r is equal to epsilon by epsilon naught, where epsilon is the permittivity of the medium and epsilon naught is the permittivity of the free space. Okay, next dielectric in an electric field. So means whenever a dielectric is placed in an external electric field, then what happens? See this. Dielectric in an electric field. So the figure 4a means this one. The figure 4a shows a parallel plate capacitor connected to a DC voltage source V0. Okay, DC voltage source V0. The plates get charged until the potential difference builds to V0. Plus Q naught and minus Q naught are the charges on the plates, and sigma is the surface charge density. And the capacitance C naught is Q naught by V naught. So see this one, the dielectric in an electric field. So here the figure shows a parallel plate capacitor. So these two are the parallel plate capacitor connected to a DC voltage source V0. Okay, so this is DC voltage source V0. The plates get charged until the potential difference builds to V0. That is the maximum. So the plates gets charged until the potential difference builds to V0. Plus Q naught and minus Q naught are the charges on the plates. So these are the charges, and plus Q naught is the total charge on this plate, and minus Q naught are this one, charges on the plates, and sigma is the surface charge density. So here see this one, sigma is the surface charge density. The capacitance of the capacitor plates C naught is equal to Q naught by V naught. Okay, let the DC source be disconnected now, and a rectangular dielectric slab is introduced into the capacitor so that it completely fills the space. Okay, let the DC source be disconnected now, and a rectangular dielectric slab be introduced into the capacitor so that it completely fills the space, which is shown in the figure 4b. The circuit is open now, and the charge Q naught on either plate remains constant, but the voltmeter shows a decrease in potential from V naught to V. When the dielectric slab is pulled out, the potential difference returns again to its original value V naught. So the charges on the plates have been not affected by the introduction of the dielectric. The presence of the dielectric has reduced the potential difference from V naught to V, and thus increased the capacitance from C naught to C given by C is equal to Q naught by V. Okay, see what happens from the figure 4b. So let the DC source be disconnected now, and the rectangular dielectric slab is introduced into the capacitor so that it completely fills the space. So here, one slab is placed, rectangular dielectric slab is introduced in between the two parallel plate capacitors. Then what happens here? The charges are, so this is a dielectric material. So dielectric material means In dielectric material, positive and negative charges are coincide with each other. So whenever this kind of dielectric material is placed in an external electric field, then what happens here? The charges are accumulated on either side of the plates. So these positive charges and the negative charges. Okay. So here sigma p. Here see this one. So sigma p is the charge density. EA is the induced electric field. Means here, due to the placing of a dielectric material in an external field, so here electric field is induced inside a material, okay, that can be represented as EI, so due to the separation of the charges. Okay. So the circuit is open now and the charge Q naught on either plate remains constant, but the voltmeter shows a decrease in potential. So charges are remains constant, but here the potential decreases. Voltmeter shows the decrease in potential V naught to V. When the dielectric slab is pulled out, from that parallel plate capacitor, then what happens? The potential difference remains. So the potential difference returns again to its original value V naught. So the charges on the plates have been not affected by the introduction of the dielectric. The presence of the dielectric has reduced the potential difference from V naught to V. So due to the placing of a dielectric slab into the parallel plate capacitor, what happens here? The charges on either side of the parallel plate capacitor does not affect it. Only the potential difference reduces from V naught to V due to the placing of the dielectric material. The presence of the dielectric has reduced the potential difference from V naught to V and thus increased the capacitance from C naught to C, given by C is equal to Q naught by V. The relative permittivity of the dielectric is measured by epsilon R is equal to V naught by V. So here, why this? So this one, V is equal to V naught by epsilon R. Okay, so therefore capacitance C is equal to Q naught by V. So therefore C is equal to Q naught by, so V is equal to here V naught by epsilon R. So substituting this V naught by epsilon R, therefore C is equal to epsilon R Q naught by V naught. So and C is equal to epsilon R C naught. Okay, so Q naught by V naught is equal to C naught. So therefore C is equal to epsilon R C naught. So epsilon R is equal to C by C naught. So epsilon R is equal to C by C naught. So C means capacitance with dielectric. C naught is the capacitance without dielectric. So epsilon R is the relative permittivity, or otherwise dielectric constant. It is denoted as epsilon R is equal to C by C naught, that is capacitance with dielectric by capacitance without dielectric. So epsilon R is equal to V naught by V. So it can be written as, so this one, C is equal to epsilon R C naught. So epsilon R is equal to V naught by V. So here V naught is equal to E naught D by E naught. So V naught and E naught and enti ikkada. So this. So this one. So here E naught is the electric field, external electric field. So D is the this one. So material which we are placing in between the capacitor plates. So therefore okay. So D is the separation between the two plates. So V naught is equal to E naught D, P is equal to ED. Okay. So D cancel అయిపోతే E naught by E. So therefore epsilon R is equal to E naught by E. Hence epsilon R is equal to C by C naught. So therefore epsilon R is equal to V naught by V, and epsilon R is equal to E naught by E. So the dielectric constant epsilon R is a dimensionless quantity. Its value is always greater than unity, and it is independent of the size or shape of the dielectric. Epsilon R is usually measured by comparing the capacitance of the capacitor with the dielectric. So epsilon R is usually measured by the capacitance of the capacitor with the dielectric to the capacitance of the same capacitor without dielectric. So that is the capacitance C naught of a parallel plate capacitor with air or vacuum as the medium is given by C naught is equal to epsilon A by D, where epsilon is equal to 8 point, the value of epsilon naught is equal to 8.85 into 10 to the power of minus 12 is the permittivity of the free space. So this is epsilon naught is called the permittivity of the free space, farad per meter. Okay, A is the plate area and D is the separation between the plates. So the capacitance C with the dielectric present is C is equal to epsilon A by D. Okay, it can be written as, so epsilon is the permittivity of the medium, that is epsilon A by D. D is the separation. So C is equal to, so epsilon naught epsilon R A by D. Epsilon R is equal to epsilon by epsilon naught. So therefore epsilon is equal to epsilon naught epsilon R. Epsilon బదులు మనం ఇక్కడ ఏం రాసుకున్నాం, epsilon naught epsilon R A by D. Okay, since epsilon R is equal to epsilon by epsilon naught, so epsilon is equal to epsilon naught epsilon R. Okay, C is equal to epsilon naught epsilon R A by D. So this is the required equation, capacitance of the capacitor. Okay, next induced charges. Induced charges. Dielectric polarization. Okay, సో ఇది నెక్స్ట్ క్లాస్ లో చెప్పుకుందాము యూజర్ ఛార్జెస్ గురించి. ఓకే, ఒకసారి డెరివేషన్ మళ్ళీ మీకు ఆల్రెడీ మెటీరియల్ జిరాక్స్ తీయించుకోమన్నాను కదా, ఒకసారి చూడండి. రైట్, సో టైం అయింది కాబట్టి క్లాస్ ఎండ్ చేస్తున్నాను. ఇంకొకసారి చూడండి, ఇది ఏదైనా డౌట్ ఉంటే నెక్స్ట్ క్లాస్లో అడగండి. ఓకే, రైట్. మెటీరియల్స్ జిరాక్స్ తీయించుకున్నారమ్మా? అందరూ కూడా మెటీరియల్ జిరాక్స్ తీయించుకోండి, రెండు తీయించుకోండి, డైఎలక్ట్రిక్స్ అండ్ మ్యాగ్నెటిక్ మెటీరియల్స్. ఇందులో మీరే చూడండి ఏది ఈజీగా ఉందో, చెప్పిన తర్వాత లాస్ట్ లో మీరే చదువుతుంది. సో మ్యాగ్నెటిక్ మెటీరియల్స్ ఈజీగా ఉంటుంది డైఎలక్ట్రిక్స్ కన్నా. సో మ్యాగ్నెటిక్ మెటీరియల్స్ చదువుతుంది కానీ అలానే డైఎలక్ట్రిక్ మెటీరియల్స్ వినొద్దని కాదు, ఇది కూడా వినండి. సో మీకు ఇది ఏంటిది ఆబ్జెక్టివ్ టైప్ కి ఇంపార్టెంట్ ద సేమ్ టైం. సో మ్యాగ్నెటిక్ మెటీరియల్స్ ఒకటి కంప్లీట్ గా చదువుతారు కానీ రెండు మెటీరియల్స్ కూడా జిరాక్స్ తీయించుకొని దగ్గర పెట్టుకొని ఇది కూడా చూడండి. ఓకే, సో రైట్, ఎండ్ చేస్తున్నాను క్లాస్. థ్యాంక్ యూ.